I'm going to turn that off though, right now.
Okay.
I don't think we need to.
For been involved with simulation for many years, both in academia and industry. And in fact, in thinking about it, I went back and I took my first simulation course in my master's program, and did my first simulation project soon after that in industry. And both of those were back when the Vietnam War was winding down. So give you an idea of how long I've been involved in doing this, and certainly seen a lot of change in the industry and the products over that time. As I said, I've been mostly in academia. I've taught in business schools, a number of business schools in the US, and engineering schools also in the US and abroad, and have been involved in a number of industry projects. Before going into academia, I was had a couple engineering positions, an IE and operations research in synthetic fiber and defense industries. And then really ever since joining academia, I've been doing industry projects and have stayed in touch with industry, and I really enjoy doing that. And that was certainly by design. And I've been a FlexSim user since 2006. So that's what, 16 years. So it's time flies. One of the things that I've always been interested in is that bridge or that link between academia or education and industry, and continue along that line and try to support that. And I think that's a really good way to bridge the two entities. And so I continue to work toward that. The other thing I've always been wanting to do is raise the awareness of the value of simulation. I see it as really valuable technology, and just would like to see it more widely used. And also always looking for ways to help people learn about simulation. Now, the webinar, the objectives of the webinar, as stated in the advertisement, is basically to introduce everyone, if you're not already familiar with it, the basic concepts of simulation. And if you already are, hopefully this is a good reminder. And we'll try to demonstrate the value of simulation and the how widely applied it is, and then introduce some of the relationships between simulation and other technologies. Before we start, a couple of things like kind of background, or what I call presumptions, that I kind of take as a given, and that's that organizational success really depends on effectively designing and managing operations and undergoing continuous improvement. But a major challenge to working in operational type systems and designing them or managing them is really understanding the dynamics, if you will, and evaluating the system dynamics that happens within those kind of systems. And but one way to do that, one way to meet that challenge, is through simulation, doing things virtually, and that's what we're going to basically talk about today. So with those kind of objectives and presumptions, if you will, the outline for today is that I'll give a brief introduction to FlexSim, the company. Then we'll talk in general about what simulation is, kind of modeling and analyzing in simulation. I'll do a short example kind of illustrating what it's like to build and analyze models within a modern simulation software. Again, we'll look at some technologies related to simulation, and then since I know this crowd might be a little bit more interested in that operation, the optimization technology, I'll spend a little bit more time on that, and then we'll open it up to Q&A. And then, of course, anything that you see simulation software-wise illustrated here is all using FlexSim. So FlexSim is
was founded in 1993 as F&H solution simulations, and became FlexSim in 2000. And the first release of the software was in 2003, and they are headquartered in Orem, Utah, and operate a worldwide network basically of distributors. And what the company provides is basically valuable simulation generated solutions for their customers in kind of a short sentence, if you will. And they do that through state-of-the-art simulation modeling analysis software and consulting services that allow their customers to analyze, visualize, and improve their real-world processes. And kind of with the screenshots and so forth off to the side, you'll see some examples, and we'll of course see a lot more through the presentation today of what the software looks like, both in terms of the model, and then toward the bottom there what some of the analyses might look like that that you'll get out of the simulation. Now, as we said, that simulation is about solving problems in operation systems. And so what are operation systems? I've been using that term, and I'll use it a lot throughout the presentation. And the simple answer to that is that's where work gets done. Now, if somebody would like a little bit more detailed definition, if you will, the way I define it is a set of related activities that transform some input into output by using a variety of resources. And this all operates or functions in an uncertain business environment. So that's basically when I'm talking about an operation system. And one of the things about them is that they're a real challenge to design these kind of systems effectively and manage them. And the reason for that is there's basically, I see it as three main reasons for why there's such a challenge. There's a lot of complex interactions, especially between all these different resources, both in terms of not just the number of items or objects that's in the system, but the interactions between them. Most operation systems include variabilities and uncertainties. Some of these are planned. You might, for example, know that an operator is going to be, say, taking a break 2 hours into the shift for 15 minutes. Well, that's a known variability, if you will, because the resource is not available. It's going between available and unavailable. So it invokes a variability in the system. And then unknown or unplanned variabilities are things like machine downtime. And things take place, they change over time. So things are changing as time moves forward. And these three things coupled together basically form what we call operational dynamics. And as you can see by the graph there at the bottom, that might be some performance measure over time. And so if you were to measure that by the dashed line, which is, say, the average of that measure, then that's probably not going to be representative in a lot of cases. And so you really need to take in the effect of those highs and lows and how they change throughout some period of time. Now, simulation does kind of mitigate those the challenges, and it does so by letting you evaluate or estimate the system performance by representing basically a model, a virtual representation of the key characteristics and behavior. And again, it's the key or salient characteristics. It's not a clone. You're not catching every aspect of that system. Again, they're too complex to do that. It does, another really good thing about simulation is it does help you understand how the system operates and all the various stakeholders to understand that. And it's a really good communication tool. And especially now in today's simulation environment where there
very visually accurate, if you will, and the 3D graphics and so forth. It allows people to better identify with the system that you're analyzing. And basically, it helps answer fundamental questions of interest to the people that are designing and managing these types of systems. Now, these questions of interest, if you will, are really about how different aspects of a system are expected to perform or behave under certain conditions or specified conditions. Now, these aspects could be things like the layout of the facility. It could be the types of processes that are used to perform work. Could be a schedule or a production plan, processing rules. These are all aspects of that system that you're interested in asking questions about. These questions are really found throughout a wide range of industries. I mean, manufacturing and healthcare and logistics and so forth. And so what I want to do is look at what are some of these ones that are more specific that we would want to kind of look at. So one would be the type of question you might ask is, will some aspect, again, some layout or some process plan or something, will it work? In other words, will objectives, both technical and economic objectives, be met, not on the average, but under specific conditions or specified periods of time? So examples of those would be, will a new, say, plant expansion meet the required throughput? And then with what confidence? Or will a proposed change result in a acceptable customer wait times? And again, with what confidence? So that's kind of, will it work? We then have, what does it take to make it work? And this some aspect, what will it take to make this objective, function according to the way we're planned? And examples of that's, what's the best way to lay out a workspace in order to meet, say, a throughput goal? Or what order should we do the work in? As a couple of examples. A third type of question is, under what conditions will some aspect not work or not meet expectations, which is kind of a risk analysis. And that is really, things like that would be, what's the chance that this production plan that we've come up with will result in us having to work overtime? Or what product mix will cause this process to become a bottleneck? Those are the kinds of questions, again, that you can ask or answer through simulation. And another one, and an important question, is there buy-in by all stakeholders? And again, that's going to be a critical factor for success. Now, one way to look at this is using simulation increases your chance of success, or you can look at the flip side of that and say it reduces the chance of failure. What's the chance that this recommendation I'm going to make may not work? And it helps you kind of quantify that and decide if that's a level of risk you want to take. As I indicated, simulation is widely applied across a number of domains. Mentioned a few already, widely applied in warehousing, discrete manufacturing, a whole host of types of business processes, transportation and, say, port operations, widely now applied in healthcare, continuous manufacturing. And again, these are just a small subset and of probably the largest percentage of where the applications are, but certainly not limited by any means to these. It's also widely applied at multiple levels within the organization. A lot of times people think, well, you apply simulation like at the work cell level only. And again, in these simulation models, here's a couple of some of the problems or issues that were addressed.
So in this automotive welding cell, what's the fewest number of operators that I can use to meet my throughput for the other production areas? But you can move up to a line and a production line. In this case, what's the best work assignments for teams? In this case, in a bus assembly line, or at a plant level, spanning the entire maybe facility. Is this was an example we did to see what kinds of improvements can we realize if we change this plant over to apply lean manufacturing. So in this case, we actually built two simulation models, one of the way it currently operates, and the second one was if we invoke or implement lean technologies, then what do we expect to see in terms of an improvement that's at an overall plant level. And then in distribution centers, it might be where do we locate products and improve our order picking process. And then we can span the entire supply chain by looking at, for example, in that particular example we looked at here was what's the best means of transportation, to move a variety of products. So again, these are all just quick examples of where simulation has been applied, and again, it's just a sampling. So let's look at really what simulation is, and it's of many types or several types, and the most common ones we'll find is first one is Monte Carlo simulation, which is probably the most common type of simulation used across a number of domains, not just operations like we're talking about today, but across all kinds of different, the sciences and different industries and so forth. And it's basically just sampling from probability distributions is the main idea, and that's about it. Then there's discrete event simulation, which is most commonly applied in operations, like we'll talk about today. And there's also continuous simulation, or sometimes people refer to it as system dynamics, which a lot of times you'll see that applied where there's, say, type of fluid flow, or where the products are such that they almost act like a fluid. And then probably the newest of these is agent-based simulation. And it's pretty common in a lot of cases that in some real projects that you'll get most of these as a hybrid. So you'll get maybe discrete event and agent, or discrete event and continuous, and so forth. And really the things that differentiate between these different types is the manner in which the states of the system change. They either change at discrete points in time, or they could change continuously over time, more along the continuous lines. And if the behavior of the system is either deterministic or pretty much constant, or they're probabilistic or appear to be random. And so these are two of the main factors on which of these different types that you might apply. And again, many problems involve, several of these. I think it's also important to think of simulation also as a blend of art and science. We oftentimes start to think, or initially think of simulation from a more science standpoint, which involves algorithms. It's got computer programming in it. It's got computer science. It involves logic, statistics, and so forth. And those are certainly necessary conditions for success. But there's also another dimension of that, which is the art side. And that is sometimes called the soft side, involves soft skills, people skills, things like that, where how do I abstract and simplify this complex system into a model that I can represent in software? Or how do I communicate how the system works, or the recommendations? And
how do I collaborate amongst a variety of stakeholders? And that's also a very necessary condition for success. So you have to have a balance or blend of both of these in almost any project. And so simulation is basically a process with stakeholders, as I mentioned. And those stakeholders, sometimes we just think of the person doing the modeling or maybe the main person they interact with, but there's a lot of people that are affected by simulation that describing how the system works, the ones that are paying for it, they're providing data. So there's a lot of people involved and they all need to be managed within the simulation project. Also think of simulation as a process, and you can really map it. Most people are familiar with the Deming cycle or Shewhart cycle, plan, do, study, act. So we can really map simulation into that, again, at a high level. So if we have those four components, the first thing, the define stage, corresponding to the plan and Deming cycle, involves some pretty important activities. In fact, some may argue that these are probably the most important, because if you don't get the objectives right, or you don't understand the system and so forth, then you're not going to be successful. So it's clearly articulating the objectives, again, to all the stakeholders, understanding how the system works, defining what the performance measures are, and the decision variables. So what things am I going to be able to change in this system to see which way is better, and what do I mean by better? What's the performance measures? And developing a plan, a project plan, and budget, and so forth to go forward. Again, most people at first would think of the next thing as I do, I go build a model. And that's true, but there's other things that can happen and should happen probably in parallel to those. I'm going to want to design the experiments that I'm going to run, or the scenarios. So these are what combinations of decision variables am I going to look at, and think about those up front. And then simulation is pretty data driven. So what kind of data do I need? And identify, collect it, analyze it, and get those three things going at the same time. Then you develop a conceptual model that you can validate with stakeholders. We'll develop that into a computer model and run some pilot runs, which then results in a programmed model, say in software like FlexSim. You want to be able to verify that it's doing as you expected. Then we'll execute and evaluate those experiments using the model, summarize the results and conclusions, and then finally we'll make and implement the decisions and assess this process. So we understand what went well in this simulation process and what could we improve better next time. Another way to kind of look at this is I like to think of simulation as a virtual operations laboratory, if you will. Again, you have an operation system, whether it's manufacturing a part or diagnosing a patient, or loading container ships, or loading and unloading in a warehouse, boarding an airplane, or helping turn sorties in a training or combat situation. So a wide, again, variety of operation systems. One or more decision makers that are both designing those systems and managing them, and they often interact just directly with the actual system itself. But if you use the simulation as a virtual operations laboratory, that becomes between the decision maker and the operation system. So the decision maker can interact with this virtual system and help them then make the best decision and implement that into the real system itself. And what that involves is, again, abstracting the key parts of that operation system, building a model, then exercising that model through analysis, and then eventually implementing the results of that back into the real system. The advantage of this is this process is non-intrusive. You could go in and change the real system. You could add an operator and see what happens over the course of a week. Well, that's expensive, that's intrusive, and so forth. You don't have to do that in the simulation if you do it virtually. The other thing is, if you make a change, you might have made a good change, but because of other things that are happening within this real environment, then it may look like after a week that it wasn't a good decision if you look at your performance measures. Well, simulation lets you isolate the change. And so in actuality, you know, if you, in that system where I said you made a change and then come back and look at it a week later, it could have been that if you made that decision, you would have, or you had not made that decision, things would have been worse. But simulation allows you to separate that out and analyze things. And also other models, analytic type models, may be a little bit faster to do, but they have a lot of typically assumptions you have to make. And a lot of times those are unrealistic assumptions in terms of the way the system operates. You can control time in the system. You can run, in a simulation, you run it as fast as you want or slow as you want. And again, in today's world, it's a very effective means of communication. Let's look at a couple of examples here of some simulation models and the problems they're trying to solve. This is one where they're looking at how well different merges and sorts happen in a fairly sophisticated conveyor system. In this clinic, we're looking at how patients flow through the system and how we might improve that flow. In this warehouse, we may be looking at where is the best places to locate certain products and what are the best ways to do order picking. In this example that we're looking at processes that involve kind of mixing and blending and batching, which might be like a food process or something where we're producing batches of a particular food product. This robotics example, but it really applies to a lot of these other examples as well, is you're oftentimes looking at the effective speeds or what batch size I use or where do I locate these, what's the positioning works best. And then finally, in this shrink wrapping example, again, another thing that is fairly generic that you look at through a lot of these different applications is what's the capacity of that machine? And maybe what's its reliability and what's the effective reliability on performance. So we talked about modeling and analysis. Let me just briefly introduce what I consider by being modeling. Basically representing the behavior of a system over space and time so that it can be analyzed. And there's three kinds of general characteristics that we try to capture in the simulation model. Physical features, which things like size, where's it located, how big is it, what's the distance traveled, speeds, things like that. The logical aspects about, what's being done, when's it being done, who does it, so forth, and maybe some steps that has to be performed as we go through that. And as I mentioned before, simulation is pretty data intensive, so we have a lot of informational attributes, and we have to maybe characterize those in terms of probability distributions or tables or something else. And we don't do that primarily on the input side, but we also tend to look at that on the output side as well. In terms of analyses, that's where we're using the output from the simulation model to answer these questions that we talked about earlier and to support decision-making and problem solving. And even though the analysis follows modeling, it should be planned early, as I indicated in that process flow, by defining performance measures, decision variables and combinations of those, which we call scenarios. And it involves experimentation and statistical inference and can include optimization. Now, since we mentioned that if any input is probabilistic, then the output's probabilistic. So that's where statistics is going to come into play. So an example here is we were running two scenarios, which is we're looking at two different product mixes and the effect on the performance measure throughput. And so in this case, 3 products are equally produced. And in this case, it's heavily weighted to whatever the third product is. And we notice that it appears that this the better of these options is the equal product mix in this example. But the other thing I want to see is that every time we run, let's say an 8-hour simulation or whatever that time period is, because of the complexity, because of variability and the dynamics, we get different throughput every time we run it. We get a different answer because the conditions are different, just like every day is different from the next. So we have to combine these, and typically we could do that through an average, or we could do that through quartiles or confidence intervals or something else. And that's where we try to capture that output or measures through statistical means. Another thing we may want to do is we might say, well, what's best? What's the best way to operate? And in that case, I've got 2 performance measures here. I had one up here, different example. One is wait time and one is resource utilization. Well, if you're the customer, you probably want 0 wait time. But if you're the company, you probably want the higher utilization. Well, you've got to balance that. And so each one of these dots is a scenario, and we're searching for what's the best combination, or the best way to operate, which scenario is best, if you will. And as we'll see here, we get basically what's called an efficient frontier, and anything along here might be considered optimal, but it depends on what your trade-off is between wait time and resource allocation or resource utilization. So that's how optimization is oftentimes used in a simulation. Let me now just go and let me show you through a quick example. And I've only got a little bit of time left, but I want to run through an example just to see how you might go through building an example like this. And so we're going to design an expansion of an operations system in a discrete part manufacturing facility. And a basic approach is we're going to build a simple small model, going to validate as we go. We're going to then add complexity as we think we need to answer the questions at hand, validate that, and then scale up to the desired size. So to fill this space that we're looking at, we have a finishing department, packaging and warehousing, and an ordering area. We're only looking and modeling right now two of these finishing machines. There may be 20 in this facility or more. Well, we don't want to build all 20 to start with. We want to get these to work, and then we can easily scale up to the number that we need. So this basic system is we're fulfilling orders. And so an order here is represented by a pallet. And so again, you could represent it by any shape that you wanted. This is a pallet, and the orders come in random times and a random mix. And we have fulfilled orders then going out. And those orders are composed of products. And we've only got 3 types of products in this little example. Again, we're testing this out that it works for different products. We had 100 products, then we can scale up to that later. The base product is these little, looks like containers. They come in randomly and at some random times, and their random types come in. And then they're basically go through this finish operation, and then have components added to them. And we've only got 2 types of components. They're either cylinders or squares. Okay, so simple or small, not necessarily, again, simple example. So the way we do this is with basic objects, a lot of this. And so in FlexSim, for example, we have this library of objects that meet certain functionality. It might be processing, it might be waiting or queuing, and so forth. And so we would use those to represent large parts of this particular model. So in the finishing, we've got base products come in randomly from an upstream process. They wait for, in this buffer, this orange area, for an operator to pick the first available machine and put them on. The operator loads it. There's a setup operation that's if the products are different from the last time they were processed. And the operators needed to do that. Once they're loaded on the machine produces them and moves them onto this conveyor. And into this, so one of these objects, this machine, there's a large number of characteristics that are built in and available in FlexSim that you can pick and change to customize it to be however your system operates. And there are a lot of these are handled either by direct input, entering a number, or most of them are drop-down menus to pick a distribution, or maybe the way you take items and whatever, the way you route them coming out. All those can mostly be handled through a wide variety of pick options. These are now another type of object are conveyors, which are used to convey the products to finishing and packaging, from finishing to packaging. The packing operation is basically as it sounds. It combines components into these base products, and the number and type of components depends on the product type, and the time depends on the product type. Then they move to a simple warehousing where they go on a rack based on their product type, and then these products are pulled to fulfill orders. And the ordering process, again, they come at random times, random quantity and random products that it's trying to pick, and they await fulfillment until they're stored on racks. And then this operator, which is a mobile resource, uses an A-star algorithm for a travel path. And what that means is we could lay out, not this example, but showing us another example. This operator is going from A to B. Well, we could lay out a path to tell that operator where to go. Or the other option is use this A-star algorithm, which we tell the operator where not to go. And the operator just avoids those particular ones that we've identified. A variety, a whole list of tools that we can use within FlexSim. And a couple of those would be, how do we schedule breaks? So there, in this case, the little sorting table turns red when there's say the operator or whatever is going on break that are scheduled. With another kind of scheduled operation might be a quality check on this machine. It's planned, it's scheduled at certain times. It's based on the clock time. So every 10 minutes, it might do a sample. It doesn't need the operator. The machine, that's when it's orange. When it's green, it's operating fine. When it's red, it's down. It's some type of failure that occurs randomly. It's unplanned. It depends on the state. It won't fail if it's not running. So it has to be running in order to enter that state, and it does need an operator to repair. The moving the items from finishing to the machine, it uses shortest processing time. And if that was the only case, we could easily do that from a drop-down menu on that object that showed on the previous slide. But we also have another condition that we don't want it to wait too long. We want the reds are the shortest processing time. Well, we don't want the blues to wait beyond, say, 30 minutes. And if they wait that long, we want to pick them up. Well, there's a tool that can help us do that called a list. And so we actually have two rules in one here. Some more tools that we can examples that we can use. Global tables are used throughout very commonly to organize and structure data. Like on the input, these are informations on the components that come in over here. Then all we would have to do is, if we want to make a change, we could come in and change one of these values and not have to go into the object itself and make that change. We could just then read it in from the object reads it from a table. Similarly, we can use use tables in output. This particular table is generating the orders we said were random. So every time it generates an order, it writes it to a table, so we could go back later and look and see what that order history looked like. The resupply of components to this packing station is done by a reorder point inventory system. And that's not a common dropdown. So we write the logic for that in what is called process flow. And we have another set of a library of different activities that we can drag and drop to form this logical flow chart. And then with each one of these activities have parameters that we can change. And so we've used that to develop a reorder point system for both of these components. Another level that you can go to is in any of these objects or in the process flow or anywhere, you can use what's called FlexScript, a subset of C++, and write your own or modify the logic that's involved. Analysis, we've seen some of this in the previous slides. If we run for single run analyses, not running replications, we can look at, in this case, we have a whole list or again, a palette of charts we can choose from that's measuring different things. In this case, it might be the contents of this buffer, wait times on the finishing machine. We can see here with the reorder point, the level of the number of items in the buffers here reflects that reorder point, so it's good validation. Same thing as the number of orders growing and how long the orders wait before they're fulfilled. And then we can do multi-run analysis, again, that we talked about before, where we're involved with experimentation. We're running multiple scenarios and we're running them for a number of replications. And then we're looking at different types of plots of those, maybe confidence intervals, or we can interact with an optimization routine. In the case of FlexSim, it's works seamlessly with OptQuest, but you can actually interact with any optimizer that you would choose. I'm just going to run this real quick. In fact, that's to see what this model looks like that we've been just briefly talking about. This is running at pretty high speed. It's actually, it's a 15-second video clip, and that represents 15 hours. You can see the dynamics of how the different measures are changing over here. And so you can run it much faster than that, or you could run it much slower, but it gives you an idea of how quickly you could perform analyses by speeding it up. And this is by no means the fastest it'll run. You can run it so fast you can't see anything happening. It just is done. So again, I see that I'm going to run a little bit short on time, so I'm just going to mention I've already talked about some of these. The interaction of tables with spreadsheets are a great way to interact and bring in tables or write out to spreadsheets. Same thing with databases. FlexSim comes with a distribution fitting software, and also you can just run your own empirical data, which means you run the data that you actually obtained from the facility itself. It's not necessarily fitted to the standard distribution. With the experimenter, you can design your own experiments and run those. I mentioned about optimization. Global information system interface allows you, especially in transportation problems, it's real helpful to use a map type interface and to get distances and times and so forth. Digital twins is a very popular topic now, especially with Industry 4.0. And FlexSim is one of the leaders in digital twins. You can test PLCs, the logic on a PLC within the simulated software. With proper headset, you can interact, you can virtually immerse yourself in a VR type environment with FlexSim. And you can also basically train, or you can use and evaluate your reinforced learning algorithms through FlexSim and its ability to connect and interact with Python. And running across all these is really data analytics. And so there's not one technology there, but many technologies would span across this. I want to save time for questions. So what I'm going to do is, this may be somewhat self-explanatory, but I wanted to show the how simulation and optimization work together. Actually, I can do a second here. It won't take me long to run through this. This example, and to give you an example of each, we use math programming to come up with the optimal schedule for a cross-dock, but tested it out under dynamic situations through a simulation model. A simulation model following input to an optimization model might be, in this simple case, deciding what the best process time is, or process time parameter, based on the outputs you got from a simulation. Simulation models can be embedded within optimization. An example we did here is we used an evolutionary strategy optimization, and it used the simulation model to evaluate its fitness function and decide what the best sequence in this case was down a production line, and each product in this case is unique. And then the last one is an optimization model within a simulation model. And that an example of that we saw already with the A-star algorithm within the simulation model. Just kind of the ABC summaries here: analyze, use simulation to analyze. And the foundation of analysis is the model. So you have to build those, and don't forget about collaborating with stakeholders. And so this is basically a risk-free environment. Analysis way beyond spreadsheets, and the 3D visuals certainly help with validation, and again, applicable across a number of different industries. So with that, before we do Q&A, I just want to say thank you to everybody for attending, and I've got a contact information here for myself and for Bill and Marcus, so feel free. If we don't get some of the questions answered through the Q&A, then we can certainly reach out to us, and we would be glad to talk with you further. With that, let's open up to questions.
Thanks, Alan. That was great. We have a question coming in. I'll remind everybody else we have a few more minutes, so feel free to put any question that you have into the Q&A box, and I will read it and have Dr. Greenwood answered. So the first question we have is, how does simulation relate to machine learning?
Well, with machine learning, what you can do is you can use the simulation itself to train come up with the algorithm, and the other side of that is it can be used if you already have a machine learning algorithm to test it out to see how it works in an actual environment, or close to actual environment, a simulated environment, and stipulate what conditions are that it has to act under to see how well it performs.
Sounds great. Another question came in. If you consider the example that you showed, how long does it take for someone to build that model and validate
Uh, that's a tough question because it really depends on the simulation on the system that you're trying to model. If it's that's a fairly small system. But again, size doesn't necessarily, it's not really a good indicator either, because it may look small, but it's got a lot of sophisticated things happening underneath. And you would build these in stages. So you might go through and utilize a lot of the drop downs, for example, that's already available in those 3D objects. And then say, well, that's not exactly what I want to represent. Then you may have to go off and build your own special logic. And, that can take a little bit longer. But the validation part is difficult as well. But I think it's certainly much faster than it has been in the past, because people can look at the model you've developed visually, and you can run it at a slow speed so they see what happens, or run it over the course of a couple of months and see if you get any situations that wouldn't seem normal. So it can happen fairly quickly, because people can really relate to this by seeing it visually of what's happening. So I think the visualization helps tremendously on validation. The other thing that can happen that's, you don't always do this, but it's advisable if you can, is if you have an existing system and you want to change it, build a simulation model of the existing system and validate it. And then people's confidence, once they validate it and say, okay, this stuff makes sense, it works. When you make the change, then you get easier buy-in. And so, because they already trust it. And so, but giving a time, it's really almost impossible to say, because it depends on what you're trying to, if it's a real simple model, I could build it in, a minute, but, it'd be real simple, but.
All right, well, I'm going to tee up one more or another one. Is it possible to create a hybrid model that uses discrete event simulation elements and rules and agent-based modeling as well in FlexSim? How can we monitor and analyze any emergent behavior in FlexSim? So 2 parts to that.
Okay. There's an agent system tool that you can use to define the agents and so forth. And then there's also a large number of, as you might have seen a little bit in that demo, of all kinds of different charts and so forth, that you can plot the things that whatever's of interest to you in terms of trying to look at that behavior. And there's a lot of predefined ones in FlexSim, that predefined measures that people commonly look at. But there's also like a stat builder that you can decide what your own statistics are, and decide and define those and collect those statistics. And then there's a large number of chart types available in FlexSim that you could then chart that and watch it evolve. Or if there isn't the chart type you need, then it's easy to export that data out to some other package that would maybe plot it the way you want it. But there's a pretty good host of charting capabilities within FlexSim itself.
Another one, can you propose case studies that combine FlexSim with mathematical programming, e.g. mixed integer programming models?
Yeah, we've done, trying to think, I'd have to, if they send me an email, I can probably give you some papers that we've done that we did just that. In fact, that example that I showed real quickly there toward the end, we did a math programming schedule for cross-docking, and we're used simulation to test it then in a dynamic environment, and also to look at ways that we could make that that math programming formulation more robust. That was kind of part of the focus of that research project, but there was and there's probably a few others I could think of. So if that person wants to just send me an email, I can get you references for those.
Okay, Christos, do you hear that? You can use the email address on the screen right now and interact directly with Dr. Greenwood about that, and he'll get back to you. And another question that has come in, I know we only got another minute. What are the FlexSim advantages among Pro Model Simulate 8 Arena?
Well, that's a, again, I think it depends. I may let Bill or Marcus address that, but I know from me, I've used some of those products, and like I said, 16 years ago, I switched, and partly because what I was trying to do, some industry projects, I was too limited, and FlexSim gave me the capability to do what I wanted to do a lot easier. And then I was just really happy with the product, and then decided to bring it into my courses. So I changed the software I was using that I was teaching, and went to FlexSim. And ever since then, they have a really good development program, so the capabilities continue to improve. And again, I work for them now, but I didn't in the past. And the customer service and help and so forth were really great. And so I never had a need to really change once I got into that. And so some of these, it'd be a little unfair. I could talk about some in the past, but I keep up with what's happening in the industry and the different software, but I'm not developing projects with them, so I don't have that intimate knowledge that I have with FlexSim. So I've just been flat satisfied with what I have, and kind of keep up just to keep up, but not in any detail that I could directly correspond. And a lot of it depends on the type of problem you're trying to solve.
That sounds wonderful. Okay, there's one last question, and I think, I don't know if this is something that will be easily answered, but could you point to demos or examples or video to see how models are deployed to end users and managed? And maybe that's something that could be better offline. I don't know, because obviously they're asking for something for like a link or something like that. But that question just came in. Could you point to demos, example videos to see how models are deployed and end users managed?
Well, there's certainly the quick answer, and yeah, there again, I'd be glad to try to find out what they were looking for in particular if they want to do that offline. But FlexSim, there's a number of, on their website, they've got some case studies that describe, certain applications that they've done and been able to write up. A lot of times things are proprietary or whatever, and they can't, but there's some out there that have been written up. There's a large number of different kinds of models that are available on the website to illustrate that. And I'm sure that if there's a particular industry of interest or a particular application, then I'm sure they'd be glad. They probably have something similar that they might be able to share. But there should be plenty of resources on the YouTube channel, FlexSim's website, LinkedIn. There's a lot of things, but if it's something in particular, we may be able to help them with that search.
That sounds good. I really appreciate it. Thank you, everyone, for joining us today. On behalf of Dr. Greenwood, FlexSim, and Informs, thank you for joining us today. A recording of this webinar will be available on our YouTube channel very shortly, as I'm sure they will be over on the FlexSim in their particular channels. So thank everybody. And anybody doesn't have and Dr. Greenwood or Bill or Marcus's contact information and still want to pose a question, it is still on the screen right now. And thank you all again, and have a wonderful, wonderful day.
Thank you.